Malkin, and my project is the development and in vitro verification of a polymersome for blood-brain barrier transport through a novel machine learning model. So the blood-brain barrier, or BBB for short, is a significant obstacle in treating neurological disease. This is because it's a highly selective membrane designed to protect the brain from foreign substances, which is typically a good thing as most compounds in the body shouldn't be getting into the brain. However, it presents a major challenge for neurological drug development as the vast majority of potentially therapeutic drugs are not able to penetrate the blood-brain barrier. Thus, finding a way for drugs to cross the blood-brain barrier is key to treating a wide array of neurological diseases, including brain cancer, strokes, epilepsy, Alzheimer's disease, and more. Recently, machine learning has emerged as a promising tool to identify drugs that can traverse the blood-brain barrier. And these studies that have used machine learning for drug permeability, they've had good accuracy and they're a good step in this field. However, their results don't address the vast number of potentially therapeutic drugs that simply cannot cross the blood-brain barrier. They can identify which do and don't, but there's still only a small minority of drugs that can cross the blood-brain barrier, and the vast majority don't. So one example of these drugs that don't cross the blood-brain barrier, which is the drug that I'll be talking about later, is doxorubicin, just one example of many, but it's an anti-tumor drug that can't be addressed by interventions like these models as it's impermeable across the blood-brain barrier. So also recently, a small number of polymersomes have been developed to aid non-permeable drugs in crossing the blood-brain barrier, but more are needed. So these polymersomes function like a boat carrying drugs from out of the blood-brain barrier across it, and except instead of the way that a boat is just on a bottom, they're a shell encapsulating the drug entirely, and they can transfer it across the blood-brain barrier since the polymer making up the polymersome is permeable. However, these current polymersomes, there's only been a few polymers identified that work with them, most of which are derivatives of one polymer, PLGA, and so this means that because of this lack of diversity, they don't work for all drugs, and the PLGA is expensive and difficult to manufacture. So in my project, in phase 1, I developed a novel machine learning model for blood-brain barrier permeable polymer discovery to find new polymers that can cross the blood-brain barrier and potentially act as new forms of polymersomes. And in phase 2, I identified and verified a previously untested polymer for drug transportation across the blood-brain barrier. So in phase 1 of my research, I developed a novel machine learning model to identify polymers likely to cross the blood-brain barrier. And for this, I trained my model on permeability data of over 7,000 compounds from the B3DB database, which was created in conjunction with the efforts for drug permeability machine learning models. And then I further pre-processed this data using RDKit's biochemical processing tools to translate the functional groups of the molecules into binary code that the computer can understand. So my novel model is a custom deep learning network that I developed in Python using TensorFlow, and it has 11 layers. So 8 of which of these are dense layers that weigh different attributes of the molecular fingerprints to determine which is most important in deciding blood-brain barrier permeability, as it's not just a single chemical marker that determines blood-brain barrier permeability, it's an array of interconnected features. And then there's 2 Gaussian noise layers, which are regularization layers that add random noise to avoid overfitting, which is when a machine learning model gets too specific to its original training data and isn't able to extrapolate its findings to new cases. And then just 1 flattened layer, which makes the output of the machine learning model one-dimensional, so it can be a single score. So my model produces a custom algorithm that scores polymers on likelihood of permeability and achieved 93% accuracy. So the way this algorithm is produced is via nodes, which make up each of the layers that I discussed on the last slide. And these nodes, they take in inputs, either the molecular fingerprints themselves, or as each layer goes on, the output of the previous layer. And then, according to a function to minimize loss, the weights are created which act as the coefficients for this custom algorithm, and they are weighing the different attributes of the molecular fingerprints to see what is important in deciding blood-brain barrier permeability. And this model achieved 93% accuracy on segregated training data, so part of the compounds I separated, didn't train the machine learning model on, and then fed back in after to see how it was performing. So my model identified ammonium methacrylate as the polymer most likely to cross the blood-brain barrier. And this is exciting for a number of reasons. So first, ammonium methacrylate is currently used in drug coating. However, it's been previously untested in the blood-brain barrier. In fact, when I called the manufacturers to get access to ammonium methacrylate to be able to work with it when I was testing in vitro. They were so excited to hear about my machine learning model's findings. They had never heard about this avenue before. It would open up a whole new window of business for them. They were so excited that they sent me the ammonium methacrylate for free to be able to use because they just thought that this was a really important type of research. So another reason that this is so exciting is if we take a look at the 13 predicted polymers that were predicted by the model to have some degree of crossing the blood-brain barrier. So most of the runners up are closely related to PLGA, which is already in use, and this serves as some validation to the model. It shows that it's on the right track because it's predicting things that are known to be likely to cross the blood-brain barrier already. But as you can see, ammonium methacrylate was predicted with an even higher likelihood of crossing the blood-brain barrier than these polymers were. So this discovery of a new polymer that can cross the blood-brain barrier has significant implications for treating neurological disease. In phase 2 of my research, I validated the blood-brain barrier permeability and drug-carrying ability of ammonium methacrylate by developing a polymersomic nanoparticle. So the drug that I was using in this drug transportation was doxorubicin, as I mentioned, a anti-tumor drug which would have potential use in treating aggressive glioblastoma. And the ammonium methacrylate forms a polymersome artificial vesicle around the doxorubicin, similar to the way that liposomes are in the human body, and together they form the amdox nanoparticle. So I encapsulated doxorubicin in ammonium methacrylate via quasi-emulsion solvent diffusion, where I mixed ammonium methacrylate and doxorubicin in methanol under magnetic stirring, and then dripped in the solution into polyvinyl alcohol, where I stirred for an additional 3 hours, and then centrifuged that solution to isolate the particles and then you can see the ATR-FTIR spectra of this encapsulation where signatures of both ammonium methacrylate and doxorubicin are shown in the amdox nanoparticle. The majority of the spectra, which is wave number and then %T, is similar to the ammonium methacrylate spectrum, and this makes sense because the ammonium methacrylate, that's what's on the outside, it's what's forming the shell, so that's what's being seen most. But then there's also signatures of the doxorubicin, and this shows successful encapsulation of amdox. So then the amdox polymersomic nanoparticle I tested on an in vitro model of the blood-brain barrier using a parallel artificial membrane permeability assay. And the way that this assay works is there's a donor well and a receiver well with a membrane in between. The membrane mimics the blood-brain barrier cell membrane using brain lipids, and the nanoparticles are put in the donor well, and if they can cross the membrane, go into the receiver well. And typically these types of tests are used with UV-vis spectroscopy to establish if there's equilibrium between the donor well and receiver well. So that was the first test that I used to establish permeability, and there's very promising results. So in the amdox, you can see the wavelength to absorption spectra with the amdox above and below the blood-brain barrier showing carrying. So this means that since there's also the signatures of doxorubicin there, it's not just that the ammonium methacrylate is going through, it's actually carrying the doxorubicin as well, and it looks very different from the blink control, which is what it would look like if there wasn't anything crossing through. But then I wanted to do further validation by looking at the components of amdox as controls. So I looked at doxorubicin, which as predicted did not cross the blood-brain barrier. This is not a surprise. It's known to be an impermeable drug. That's why I was using it. And the below the blood-brain barrier looks very similar to the blink control. And then with the just ammonium methacrylate, however, I ran into a little bit of a problem in that you can see even in the above the blood-brain barrier, the spectrum of ammonium methacrylate just happens to look very similar to the spectrum of the blink control. So even though I knew that ammonium methacrylate must be crossing because the amdox was crossing, I wanted to be able to further validate this and increase the specificity of the assay. So for that, I increased the specificity using ATR-FTIR spectroscopy because this would be looking at the actual chemical structure rather than just the light spectra. So here for the doxorubicin, again, no passage across the blood-brain barrier, not a surprise. Below the blood-brain barrier, it looks like the blank control again. And then with the ammonium methacrylate, now not running into the same problems anymore, it looks very distinct from the blank control, and we can see this clear passage across the blood-brain barrier.
Ashley, you have just under 2 minutes left.
Okay, thank you. So I then used ATR-FTIR spectroscopy analysis to show MDOC's blood-brain barrier permeability as well as secondary validation in addition to the UV-Vis spectroscopy. So here we can even see the distinct ammonium methacrylate and doxorubicin signatures in the MDOCs, with ammonium methacrylate circled in blue and doxorubicin signatures in red, and we can see it crossing yet again. So the previously untested polymer identified by my machine learning model of ammonium methacrylate not only was able to cross the blood-brain barrier, but it was also able to transport doxorubicin through the blood-brain barrier as well. So this research has dual novelty in both machine learning and in drug development, because in phase 1, I created a novel machine learning model for polymersome development, something that has not been done before, and then in phase 2, I discovered and demonstrated that ammonium methacrylate, a polymer previously unknown to blood-brain barrier research, can not only cross the blood-brain barrier, but transport doxorubicin across through this development of a polymersomic nanoparticle for blood-brain barrier traversal. And both of these phases developed novel products which may aid in delivering treatments for a wide array of neurological disorders, doxorubicin targeted to brain cancer, but in the future I'd like to test ammonium methacrylate with other non-blood-brain barrier permeable drugs to expand its carrying power beyond doxorubicin to look at drugs related to Alzheimer's disease, epilepsy, strokes, and more. And I'd also like to validate other polymers predicted to have a high likelihood of permeability by my machine learning model, and I'd like to use my machine learning model to determine permeability of a wider range of polymers. So I'd like to thank my science research teacher, Mr. Andrew Bramante, and Dr. Radhika Patel for their invaluable support throughout this project, and I'd like to extend a huge thank you to Connecticut JSHS for the absolutely amazing opportunity to present my research here. So these are my references, and do you have any questions?